Hello everyone, we will like to talk about the distributed force and how can we find two things. The sum or the resultants of these forces, whether they are uniform distributed or linear distributed or has a function, we would like to get the resultant. That's number one. Number two is to find the point of application as well. So if you have this kind of loading right there, we would like to get the equivalent load force F, and we know at what distance that will be from the support. That is basically what the intention is. Conceptually, if I ask you for what is the resultant force due to the distributed load, and the resultant force due to the distributed load is equivalent to what? The centroid or the arc length or the area under the distributed load, meaning what can we say about this? How can we find the resultant force for that kind of distribution of the load? It's equivalent to the area. So if you find the area of that shape, that will give you the resultant force. So the answer is C, is the area right there. However, other than the value of the resultant force, what is the line of action of the distributed force? If this is uniform distributed, then the line of action will be at the center of it. But the line of action for the distributed load here, it passes through what? The midpoint or the right or the left or centroid? The answer, of course, it will be in the centroid of this area. I just wanted that to be understood and clear to us so that we can identify that later on. An example also, if you have a uniform wind is blowing against the side of that triangular sign, you see that kind of wind pressure that's applied on this sign, we would like to find out how much force it's applied and where the point of application. Why is that? It's like when you open a door, there is a force applied at an offset position from the hinge, and that will cause rotation. It's going to apply certain moment. Same thing here. I'd like to get the equivalent load of this distributed load, and I'd like to get the point of application as well. So I believe the centroid of this shape will be the point of application, and the area or the volume of that shape will give you that kind of force. If you have any kind of scenario where you have a function of the force itself, so there is an equation for that telling you that the force is nothing but the integration of that function. So it's the integration of d sub f. So if the force itself has a certain function wx, then the integration of wx with respect to x is the force, which is nothing but the area. So the area of the shape is the force. The question is at what location, and that's what the next equation is. You use the moment in order for you to find the location of the applied force. So I will make it like I did in the lecture, which is like that. That's a very simple two equation that you can use. The area of that shape, which is the integration of w or p of x, that will give you the force. However, the point of application at a distance x is nothing but integration of wx times distance x dx over the integration of wx dx. The top part is the moment, the bottom part is the force. As simple as that. You can apply to any kind of shape of forces. However, if you have that as a uniform load like this, life is easy. If you have uniform distributed load of 400 pounds per foot, and we ask you what is the equivalent force and at what point, all you need to do is multiply the 400, which is the vertical, times the 10. 400 times 10 gives you 4,000. That is the force. At what location? Midpoint, which is at 5. So done with the top part, okay? How about if in the test I give you that triangular shape? I say it starts from 0, goes all the way to 600 Newton per meter. What is the total load? You can say I can do integration or I can do summation, which is the area. What is the area of a triangle? 1/2 base times height. 1/2 6 times 600, that will give you 1800. At what location? It's going to be at 2/3 from the vertex or 1/3 from the base. So if this is 6 meters, it's going to be 4 meters from this side. It's so simple and straightforward, and I urge you guys to be able to solve that. And the way, if you wish to do it, this is exactly what I did earlier, which is the area, and you take the moment at certain point and you simply say force times distance x that I don't know equals the reactions time that distance, and you can find this. Or if you know what the centroid is for triangle, you just say 2/3 and 1/3 and you're done with that. This is basically something that you should be able to do if you have uniform and you have linear distributed. How about if you have something like that which is combined, this linear distributed load and uniform load? I assume I'm going to divide it into two pieces, triangular shape with an equivalent force and rectangular shape with another force. So you have two forces right here. I can find out the support reaction, one unknown and two unknown. How? Use sum of moments, sum of x, sum of y, and you're done with this. I think that is very useful for you to play with and just identify and be able to solve the problem accordingly. If I give you in a test something like that and they ask you what is the force, is it 12 or 100 or 600 or 1200? Let's see, 1/2 base times height, so 1/2 12, which is 6 times 10, that is 600. So the answer is C, 600. So simple, right? At what point of application? You can just say 2/3 of that if you wish, or rather 1/3 from here and 2/3 from the vertex, and that's basically it. So what is 1/3 from the base? 1/3 of 12 is 4, so the answer is B. You can do that, or you can just say sum of moment about the left support equals 0 equals FR, which is 600 times X, minus FR times X plus the force at the right end times the whole length 12 equals 0. And you know what that force is and what force is 1/3 and 2/3. So in this case you can find this, but honestly, centroid of the shape 1/3 from the base, so the answer is B, which is 4 meters. I hope that gives you an idea of what we're trying to solve, and I urge you to just know these two equations that you're going to be using, and they are very simple. One of them is the total force and the other one is the moment. So the moment equation is like this, which is basically m over force, gives you the point of application x, and the sum of forces, which is basically from this equation that the force is the integration of wx dx. Thank you so much.